Hello everyone, welcome to Dakshana e-classroom program. So today we are going to start a new chapter, and that is about electromagnetic induction. In short, we call it EMI. This is also like very interesting chapter, and here you will learn a lot of new things, a lot of interesting things. See, in this world you can imagine now how much we require electricity, right? Like in this time we can't imagine our life without power, without electricity. Everything we like living is run by electricity, is it? So next point is how electricity is produced, is it? It's like magical things. Actually, you will understand some magnets are there, some wires are there, some coil is there, and when some coil is rotating in the magnetic field, electricity is generated, right? Can you just imagine how interesting it is that some magnetic field is there in that region? If you're keeping one coil and rotating it, and you will have electricity, you will have current, you will have potential difference. We will try to understand why and how this exactly, like how this happen, how that electricity gets generated, and we will understand a lot of things related to exactly that, that is working of motor, generator, that also comes under this. And all these things actually like initially started with Faraday's, because Faraday's observed some experiment, did some experiment, and based on that he like got some conclusion. Okay, this is this, all those things are happening, and we will try to understand those things. We will also try to understand some inductor in a tube light, is it? I think everyone might have seen there is one small some cylindrical element, something like that is there. Many of you might have seen it. This is called inductor. This act like you will understand what is exactly that and how it exactly work, what is the function of this actually. So we will understand. So like what is exactly inductor. So a lot of things are there in this chapter, we will try to understand. So before starting this chapter we need something actually, and that is magnetism. So we like I'm assuming that you have gone through like the magnetism chapter, and you are remembering the formula of magnetic field for different situations. Magnetic field due to current carrying wire, magnetic field due to a coil, is it? Magnetic field due to a ring, and so on, like different things. And magnetic flux also, but still I will try to explain a little bit about magnetic flux. So this is about a little bit about this chapter, and we will see a lot of things about. I hope you will enjoy, you will find it interesting. It's definitely not boring chapter, it's quite interesting. If you like, we normally do not have exactly experimental setup. Otherwise, if you do it in the laboratory, and definitely you will be finding it very fascinating. It's like a lot of things are there, you will find just wow, like it's so much interesting things are there. But we will limit our everything discussion only up to the board. You can go for some like videos on YouTube, you can check about like things working of motor, generator, and a lot of things are there. And is it how flux, EMF, and generated, all those things you can actually like look for some videos or experiment available on YouTube. Okay, so this is about that chapter. For that you require a magnetism. So you have gone through that chapter. I'm assuming that you are remembering the formulas. If you are not remembering, I would advise you to please just go and revise the chapter so that you are familiar very well with the magnetism concept, magnetic field due to different systems. Okay, so by this time you all are done with that part. Now we are going to start this chapter, that is electromagnetic induction. So you will require one more thing actually, I'm going to explain you. It's like just important tool sort of, and that is basically your area vector. It's a small concept, but it will help you. It will not be like it's not much required in this chapter, but it will definitely help you. It will make you like things easy for you to understand actually. So that's why I thought it will be helpful. So first thing is vector. Very well, everyone is familiar. It has magnitude, it has direction, right? If I say force, so let's say I denote force, this length of this arrow is denoting the magnitude of this force, and direction means force is acting in this direction, and we write it F bar. So you know actually the force is acting in this direction, and its length will be representing its magnitude, and that is how we can write force as a vector quantity, right? So this is in area, things are little bit different, because if I say, let's say this is one plane, Okay, side A and A, so it's a square. Then area of this square, its magnitude is given by simply A square. Now, point is, where is the direction, right? So the point is here about direction is, because you have not seen it, even if you have seen it, that's good thing. So the thing is, we are conventionally, right? What I'm telling you, just take it and accept it. Okay, so conventionally in this case, because it's a plane, so here the direction of this area vector is given by a normal to this plane, right? So that normal will be either outward or it can be inward also. Understanding? So this is the direction. This, if I'm taking this is the plane, then its area magnitude is given by this and its direction will be this. It help you in understanding exactly just like normal. If I'm having one vector this, then I can resolve it into two component. This is, let's say, a vector, then I can write it's ax and this is ay, is it? So two components I can resolve. This is theta, so I can write ax is equal to what? A cos theta. Ay is equal to a sin theta. So if we are having this is a vector, then two perpendicular components of any vector can be resolved. Exactly in same manner for this also we can resolve into components. Okay, so first thing is, yes, area is a vector quantity. Area is a vector quantity. Magnitude you already know. Simple calculation. You are already aware of that. Is it? Not going to tell you about. Yes, direction. So direction of area vector, it is conventionally taken along normal to the plane or area. So if I take this is my area, let's say, then direction of this area vector will be either this pointing outward or cross pointing inward. Means this direction of this vector will be normal to this plane. So normal is along this, so direction of this area vector will be outward. So we can write a bar is equal to some, let's say, magnitude and a cap, is it? Just like this. So in this situation, just try to imagine here, like here I am having one just imagine this. Okay, so let's say this is our one geometry. Here I am taking its side as A and this is also A. So it's a pipe of square cross section and its cross sectional area of cross section is given by A square, right? So if I'm taking this area, then the cross section, then its area will be also this one. Now if I'm taking a cross section like this, is it? A cross section like this. I hope you can imagine it easily. So this, if I'm defining it's A, B, C, D, E, F. Then here I can write area of A, B, C, D is simply A square. And let me take this direction also, just to make it simple, the calculation. It's A, this is also A, and I have taken this is also A. So what means DE is also equal to what? A root 2. Is it clear? Alright, so now direction of this area vector, if I am looking at it triangle AED from this side, then this wedge shape geometry will appear like this. Okay, so this I am also taking a, and this is also a, and you can write this is a root 2, and here this will be like a comma b, this is your d comma c, and this will be your e comma f. Means here e is in front and f is in backward. So if you are looking at it, this Vedic geometry from this side, then it will appear like this. So now in this case, direction of this area vector means this area means direction of this plane will be normal to this, and that is along this direction. And here I can write, actually, if this angle is 45 degree, because it's a, so here in that situation this will be 45, this will be also 45. Is it clear? Now see, we can verify it. So in this situation, area of plane E, F and C, D, this you can write its width is what? This A, and this one is A root 2, so you can write this is A square into root 2. Clear? I know this area, this ABCD is A square. Clear? And see, its area vector along this direction. If this is, let's say, my area vector, is it A bar, I can resolve it into two components. So this will be like A cos theta, and this area will be A sin theta. I hope you are understanding. Now just imagine, this is what direction of area vector means. This should be along normal to the plane, and that will be along which plane? This normal will be along which plane, or this normal will be for which plane? You can just imagine this will be for this plane, means that will be for ABCD plane. So I can write area of ABCD plane is given by A cos theta, right? So here I can write area of plane ABCD, this is equal to A cos theta, and here you know actually theta is equal to 45 degree. So I can write, and A is what? This is A square root 2. So this implies A square root 2 into cos 45 root 2, and that is coming out to be exactly A square. And you know this area is also A square. So actually if we are dealing in terms of vector, we get exactly same thing. Simple thing for you is that if any normal surface is there, so let's say this is your normal, is it? This is one surface. Simple thing, its direction of this area vector will be normal along this. You can take it outward, you can take it inward also. So direction will be along normal. Now if I am resolving it into component, so let's say this is some like component, just like here my net area vector is this. Now I am resolving it into components, A cos theta and it's A sin theta. Now the point is, this area will be of which plane? So now for that you need to see that for which plane this is the normal. You can see for ABCD plane this will be the normal. So that's why this area is actually for which plane? Plane ABCD. Now you can see here also A sin theta. Now this normal will be along which plane? ABFE. So that's why this A sin theta will be the area of which plane? That will be ABFE. I hope you are clear with. So in general term, so I can like, first thing is area vector, just normal we can resolve actually. So here in this case, if I am writing this area as, let's say this is A1, okay, and plane okay, area of plane A B F E, this you can write A sin theta, and that will also come exactly, this is let's say A1, it will be also A square into root 2 into 1 by root 2, and that will be A square. Let me write it A2. So here we can write actually A square is equal to A1 square plus A2 square, because it's normal perpendicular, just like normal vector. Is it? So same thing is here also, we can resolve into component, perpendicular component. And in this situation, see, let's just consider this condition. So here I am having one pipe of circular cross section and its area is A, okay, and here so I can just take this area will be A, and now if I am taking this is my another plane, right, then you know actually its area vector will be along this front. I am taking it A prime, and let's say angle between this is theta. Then what I can write, my A prime cos theta will be equal to what? A. I hope you can imagine. A prime cos theta, so means this is the area, slanted area. If I am taking component along this, A prime cos theta, A prime cos theta means it's normal to this plane, so means this area is equal to this area, so A prime cos theta is A, and from here you can write the relation between this theta and this area and this area, and that is A prime is equal to A by cos theta. Clear? So that way, like, we can relate the area vector, and many time it make things very easy for you. So I hope it's little bit about area vector. You read more about if you are still having confusion. Otherwise you don't need much more about this, but yes, you should know the things actually, because I will be writing few relations. Then there you may be wondering that how I write it A cos theta as B into ds cos theta. So for that purpose, I hope by this time, like if you are understanding this, then you will not be wondering about that point. Okay, so this is just a little bit about area vector. Let me come back to that point, that is electromagnetic induction. So let me just erase it first. Okay, so the next is magnetic flux. First, let me tell you what is exactly magnetic flux, because we will require it a lot. Is it? So magnetic field lines, right? You must be understanding, you must be clear with that. Magnetic field lines, some imaginary curves, is it? Like in the direction, or you can write the tangent to those curves gives you the direction of magnetic field. So to just imagine magnetic field, we draw magnetic field lines, is it? And now magnetic field line intensity is proportional to magnetic field strength. So here we define a magnetic flux that is equal to, it is the number of magnetic field lines crossing an area normally or perpendicularly. That is defined as magnetic flux. So here, see, the thing is, let's say in some space these are magnetic field lines existing. Okay, so magnetic field lines like this, and if I am taking some area like this, then so let's say its area is A, and I'm assuming that it's like these magnetic field lines are crossing this area normally. So magnetic field lines are cutting the area A normally, right? And magnetic field is B. So here now you already know that magnetic field lines, I am saying the magnetic flux is number of field lines crossing the area. So in number of field lines, we actually do not count the number 1, 2, 3, so on. We write the number density of field lines is proportional to the magnetic field strength. So that way, if field strength is higher, means more number of field lines will be crossing same area, the density will be higher. So in simple terms, here I define the magnetic flux quantity phi. This we write with term phi, and this is equal to B, magnetic field into area, because I am saying the number of magnetic field lines crossing the area normally. So number of field lines is proportional to B, and mathematically we write B into A, or we also write it's B bar dot A bar if it is in vector form. So this is, and its unit of magnetic flux unit is called Weber, and it's denoted by WB. S, this is also SI unit, SI unit of magnetic flux. There is a CGS unit also, that is Maxwell. Maxwell is the CGS unit, and 1 Weber is related to 10 to the power 8 Maxwell. Okay, so and we also write unit for B, magnetic field, is Tesla, and area it's meter square. So we also write 1 Weber. This is we sometimes write Tesla into meter square, right? So that is the measurement. Next point is that if, let's suppose, magnetic field lines are not crossing a area normally, so just imagine this situation. So let's say we have this plane, and so I hope you can imagine it, and this is the plane, and now exactly A, B, C, D, E and F. Clear? And here let's say magnetic field lines are crossing it like this. So now just imagine, for area ABCD or plane ABCD, I can say these magnetic field lines are crossing it normally, and I will write the area of the plane ABCD. Let's say it's A, capital A. This area of ABCD plane, let's say it's capital A. Magnetic field strength, it's capital B. Then flux through ABCD plane, I can write it's B into A. Clear? And here you can see if they are crossing ABCD plane normally, and this is 90-degree angle, that means this plane ABFE will be along the, so if this is the magnetic field line, then plane ABEF will be this way. So you can just imagine here, no magnetic field line will be cutting or crossing this plane ABEF. Crossing means if I am saying this is something like, let's say some plane, the magnetic field lines should cross it this way actually. Yes, they can cross at some angle also, but not this way. If they are going in this direction, then no magnetic field line is crossing this area. In that situation, flux through this plane will be 0. Area will be there, magnetic field will be there, but because they are not crossing it normally, that's why the flux through this plane in this situation, if field lines are passing like this and this is the plane, in that situation magnetic flux through this plane will be 0, right? So in this situation here I can write flux through ABEF will be 0. And now see here actually, if I can say like ABCD is perpendicular to magnetic field, then you can just imagine here the number of field lines crossing this ABCD will be exactly equal to the number of field lines crossing CDEF, but the area of CDEF is different, right? So here you can write this, and number of field lines, I can write number of field lines crossing plane ABCD is equal to number of field lines crossing CDEF, right? But area of the plane CDEF is different, so means the flux should be equal. But if I write the flux simply magnetic field into area, that will become different, is it? So that's why we need to write it in terms of area vector, or in this situation. So if I am taking, let's say, let me imagine it from this side, so I can write my magnetic field lines are like this, and okay, and this will be A comma B, this will be D comma C, and this is E comma F. So this wedge shape geometry, this will appear like simple triangle when we are looking at it from this side, and magnetic field lines will be this, and here you can just imagine this plane is having same flux as this plane. So number of field lines cutting this plane means ABCD is exactly equal to the number of field lines cutting or crossing this plane, is it? So if I take, let's say, the area vector of this plane will be along this direction, and I am taking this angle as theta, is it? So this is the field lines, so I am taking this angle as theta. In this case, the angle between area vector CD of area CDEF and magnetic field is theta. If angle between magnetic field and area vector this is theta, then you can easily resolve here actually. So flux through this, is it? Now I am taking, let area of plane CDEF, let me write it capital A, and this angle theta, so you can resolve easily. So this is equal to what? A cos theta, and this will be A sin theta. So you can write the flux through A sin theta means this plane is definitely 0, and then here I can write flux through plane CD EF will be equal to what? This I can write in two ways. It's B into, that is equal to this area also, and this area is what? A cos theta. So I can write B into A into cos theta, and A is the what? A is the area of CDEF. So this flux means phi flux through CDEF is equal to B into A into cos theta. And you can write cos theta is what? Angle between B and A bar. So this can be written as B bar dot A bar. So that way we can write actually flux in terms of dot product of area vector and magnetic field, and you can see here exactly. So this area is what? A cos theta. So you can write magnetic field into area vector, that is A cos theta. If I am writing this is, let's say, A1, then you can write this is also equal to what? B into A1. So it's exactly same thing. So in simple terms, magnetic flux is given by dot product of area vector and magnetic field vector, and where like theta, you know, it's the angle between area vector and magnetic field. So in general term, let's say if this is some plane, okay, and its normal is, let's say, along this, but magnetic field is along this. So and theta is the angle, this is A bar and this is B bar. Then flux through this plane phi is given by BA or B bar dot A bar, or you can write BA into cos theta. So if I am writing it this simple this way, now I think like you should be understanding, you should be getting it, that why this theta and from where, how it is coming, that is because of area vector. So I think like by this time you should be just simple clear what is the magnetic flux, that is equal to simply B bar dot A bar or B dot like dot product of magnetic field into area, right? That is written as. So in this situation, if magnetic field is not constant or means it's varying, that means like let's say this is somewhere field lines density is also not constant, that automatically prove magnetic field is not constant. In this situation we consider one small area, let's say this is and its area vector is ds bar and this is B bar. Then flux through this, that means d phi, we will write dot product for this small element, that will be B bar dot ds bar, is it? And the total flux is given by phi, that is integration of B bar dot ds bar, and this is your magnetic flux. So in case if B is variable, we can go with the integration part for B dot ds bar, and if it is simple, then you can multiply, or if there is angle between area vector and magnetic field, then we need to go with the dot product of B bar dot S bar or dot A bar. Sometimes we write area in terms of S also. So this is just about magnetic flux. Let's next see some experimental observations or experiment that Faraday did, and from where he observed something like some flux or some like current EMF in the circuit, and then he finally wrote some conclusion, and we study them as Faraday's law of electromagnetic induction. So let's just see the experiment first. So next was Faraday's experiment of EMI or Faraday's observation. So what was those? He made some simple setups like this. He took one coil and connected one galvanometer to this coil like this, galvanometer, and took one bar magnet. So this is, let's say, bar magnet, north south pole, and then what he did, actually he moved the bar magnet. So now what is happening actually here in this situation? See, this is bar magnet, this is a loop. Now what is happening when we are bringing it closer? Some magnetic field lines are passing through this loop, so definitely some flux is linked to this loop. And what he observed was that, let's say when he is holding this magnetic like bar magnet, there is no deflection. Simply holding it at one point, there is no deflection in this galvanometer coil, is it? But if he is moving it outward or inward, or basically away from the coil or towards the coil, in both cases he was observing some deflection. So when the bar magnet is moving away or towards the coil, there was deflection observed in the galvanometer. So that is one setup. Similarly, what he did, he made another setup just like this, and here he just this switch and connected one battery like this, and rheostat, and this way. So he connected, and so what is happening, see here, when this switch is on, this is battery, there will be current in this coil. Current is in the coil. Then from the chapter magnetism, you must be knowing a current carrying coil also act like a bar magnet. So in this case, what will happen? This magnet will also generate magnetic field lines, right? Like this way. So here also, depending on direction, magnetic field lines will be there. Now what is happening? I am placing another coil here and connecting it to galvanometer. Connecting this coil to galvanometer. And now if I'm just keeping, let's say, this point here, some flux will be linked initially. So when you are switching it on, there will be some deflection. But if you just keep it on here and there is no like switch on off, it's in on condition, keeping it, some constant current is flowing in the loop, there will be some magnetic field lines and there will be magnetic flux through this, and this flux will be linked to this coil also. So in that situation also, when we are not moving this like rheostat, we are not varying here. Changing the rheostat means we are changing the current in this coil. Changing current is linked to the coil means the magnetic field strength or magnetic flux, magnetic field lines are changing. So that means some changing flux is linked to this coil, and when changing flux is linked to the second coil. In that case, there was deflection in the coil, and when there was some constant flux linked to the coil, there was no deflection in the galvanometer. So here he observed when a changing flux is linked to coil 2, let me write this is coil 1 and this is coil 2, then there was deflection observed in galvanometer. So whenever there is some changing magnetic flux is there, then there is some deflection. So these are like two of the experiment setup. There are many different possibilities can be there. So from these setup, is it from here also we can write some conclusions, and those conclusions was actually written by Faraday's in the study them law of Faraday's or Faraday's law of electromagnetic induction. So those were all just result of these experiment. Let me write those results. So those observations Faraday's wrote as Faraday's law of EMI. So first law was whenever a conductor cuts magnetic field lines or magnetic flux through a coil or conductor changes, EMF is induced or produced in the coil or conductor that is called induced EMF, electromotive force. This induced EMF persists as long as changing magnetic flux is linked or magnetic field lines are cut by conductor. Means the change in the flux is important. It's not flux. I'm like, if we are having, let's say, one coil, one conductor, and some magnetic flux is passing through that coil, but that flux is constant, in that case also there is no EMF induced in the coil. So whenever or up to the time or as long as the changing flux is linked to the conductor, to the coil, then induced EMF is existing, EMF is produced. Once the flux passing through it, a conductor, a coil, is either zero or it's like constant, there's no induced EMF, right? So simply this we call, like, whenever a conductor cuts magnetic field lines or a magnetic flux through a coil or conductor is changing with time, is it, or changes, EMF is produced in the coil and conductor, and this is called induced EMF. This induced EMF persists as long as changing magnetic flux is linked or magnetic field lines are cut by the conductor. Once like their flux is constant, there is no EMF. The second law was, so next comes is like, okay, EMF is there, then how much is it? So the induced EMF is equal to the time rate of change of magnetic flux through the coil or conductor. So the EMF magnitude, it's given by d phi by dt, and here minus sign is also there. So the magnitude of EMF is the time rate of change of magnetic flux, and minus sign here, negative sign, implies the direction here means polarity of EMF, or you can write direction of current will be such as to oppose the magnetic changing in magnetic flux. So negative sign here implying the direction, or basically the polarity of induced EMF will be such as that it opposes the changing magnetic flux or change in magnetic flux, or the direction of current will be such as it opposes the change in magnetic flux. So this is about law of Faraday's law of electromagnetic induction. Electromagnetic induction is basically, you can write cumulatively, this phenomena that when a changing magnetic flux is linked through a coil or a conductor cuts the magnetic field lines, some EMF is induced in that conductor. This phenomena we also call as electromagnetic induction, and because it was studied by Faraday's and the conclusion was given by Faraday's, so we also study them as like Faraday's law of electromagnetic induction. So this is, let's see some like basic application so that it's like more clear to you of this concept, Faraday's law, then we will see next. Okay, let's see some application of Faraday's law, so that will like these examples will help you in understanding even better things or better Faraday's law. So let's see one example one. So a coil is placed in constant magnetic field, a constant magnetic field like this, B is existing and coil is placed like this. The magnetic field is parallel to the plane of the coil as shown. So this coil is this way and magnetic field lines are like this. Then you are asked to find the induced EMF in the coil. So I hope you can answer it easily. You can see what is the magnetic flux through this coil, and the answer is 0, right? Because no magnetic field line is crossing this plane. They are in the plane of the coil, is it? So you can write here phi through the coil is 0. When flux is 0 and it's not changing, what it implies, so d phi is also 0. This implies EMF induced will be 0. So when field is there, coil is there, but there is no flux and no change in flux, then EMF induced in the coil will be definitely 0, right? So I hope that makes sense to you. Let's see next example. A magnetic field is perpendicular to the plane of this coil. Here this cross means the magnetic field line is inward like this. They are going inward. And this is coil, area of the coil is A. So magnetic field is perpendicular to the plane of the coil and constant. So here magnetic field is constant, and then you are asked to find the induced EMF in the coil. Okay, so let's see here. Magnetic field is B, area is A, and they are perpendicular like means, so what I can write, flux is equal to what? B into A, simple, because both are B and area vector normal, they are in same direction. So flux is given by B into A. Yes, flux is there, magnetic field is there, EMF is magnetic field is there, area is there, coil is there, and it's crossing the coil. So that's why flux is also there. But if I write delta phi or d phi by dt, what is that actually? So you can write this is 0 because no flux is changing, magnetic field is constant. So that's why number of field lines crossing this coil is constant. So the change in magnetic flux is 0, and that's why you can write here EMF is 0. So what it implies, even when there is magnetic flux but it's constant, it's not changing with time, then also in EMF induced or induced EMF in the coil will be 0. So the point is, for EMF to be induced in the coil, magnetic flux must be there and it must be changing with time, then only there will be EMF induced in the coil. So if flux is there but it's constant, there is definitely no EMF induced in the coil, right? And let's see next. Find the direction of induced current in the coil. Magnetic field is perpendicular to the plane of the coil. So here B is the magnetic field and it's perpendicular to the plane of the coil, and it's increasing with time. So here you can see B is increasing, means dB by dt, it's some, let's say alpha, it's constant. So B here it's not constant, B is changing, magnetic field is increasing. So now here you can see, yes, there is magnetic flux, there is magnetic flux changing with time through the coil. So definitely EMF will be there, is it? So first thing is for third part, okay, let's see. So here we have coil, magnetic field B, area A. So if I can write phi is equal to what? B into A, and then d phi by dt, if I write, then this is equal to, area is constant, dB by dt, minus will be there. So d phi by dt will be what? Or minus of d phi by dt, and that will be equal to minus of A into alpha. So this is the EMF. So yes, in this situation EMF induced will be there, and it's given by minus A into alpha if I am taking dB by dt as alpha. In that situation, this is the induced EMF. Next point is, what will be the polarity or what will be the direction of current flowing in this coil due to this induced EMF. For this point I explained here in the last part, in the concept Faraday's law, that negative sign implies that induced EMF will oppose the changing flux, and try to understand that what it means exactly. Okay, so see it here. First thing is, what is the direction of flux? Here flux is in which direction? Means like you can see magnetic field lines are inward, is it? So magnetic flux is inward, field lines are inward and crossing. I will say, let's say at some moment of time 10 field lines are crossing, and what it is saying, it's increasing. So if magnetic field is increasing, what it implies, the magnetic field lines will be also increasing, or I can simply say the flux will be increasing. So just to make you realize, just to make you understand, I am taking, let's the number of magnetic field lines crossing this area at some moment of time is, let's say, just to make you understand, it's 10, and now it's increasing with time. So number of field lines after some time will be what? 11, 12, 13, 14, 15, so on, and this is increasing. So flux through the coil is increasing, and that's why there is EMF, and that is magnitude given by this minus of A into alpha. Next point is, like, what will be the direction of induced current? So the current will be induced in a manner such that it should oppose this changing flux. Changing flux, oppose means flux inward and increasing. So oppose will be what? Means the induced current should induce or should generate a flux in opposite direction. Clear? Means flux due to field is inward, so the current should induced in a way such that it should oppose the magnetic flux, and when it will oppose, when the flux due to the induced current is in opposite direction, means outward direction. right? And a current carrying coil, we can find the direction of magnetic field or north pole by right hand thumb rule. Curl your fingers in the direction of current, thumb will point you in the direction of north, is it? So here magnetic field is in inward and I want the opposition, so means the magnetic field should be outward. So you can see here the current should be flowing like this way, means it's anti-clockwise. Then induced like a current or magnetic flux due to the induced current will be outward and it will try to oppose the changing magnetic flux. So here I can write the direction of induced current in the coil should be anti-clockwise, right? So if direction of induced current in the coil is anti-clockwise, then what will happen? The EMF or the flux due to this current will be outward and it will oppose this magnetic flux, and that's what exactly Faraday's law says. So that's why we can get the direction of current induced in this coil will be clockwise, and that's your answer. So I hope you understood this point, that how we find the direction of induced current in the coil. You need to decide that in a way such that the changing flux linked to the coil should be in opposite direction, or you can say the current induced in the coil should oppose the changing flux, right? Let's see one more example. So I hope this point of induced direction of induced current will be more clear to you. Okay, so here we have one more example I can erase. So a long constant current carrying wire is there, is it? So let me explain you. So here let's say we have a very long means infinite current carrying wire carrying some current I. Now by this wire you should be knowing from magnetism that what will be the direction of magnetic field and what will be magnetic field at any point. So you can write it again by right hand thumb rule. We align the thumb in the direction of current in the wire and then curl your fingers. That will give you the direction of magnetic field. So here you can see the magnetic field lines will be inward, and B due to infinite current carrying wire is mu naught into I divided by 2 pi r. So here you can say B is inversely proportional to R. So means field strength will be here. It will be higher compared to here, compared to here, compared to here, right? So as we are moving away from the wire, our field will keep on decreasing field strength. Now let's look at loop 1. So loop 1 is there. And yes, you can see magnetic field is inward, area of the loop is A. So phi will be there, B into A. Here remember, B will not be constant as you are moving from this point to this point, so it will be changing. So that's why to find the flux we need to find it by integration dA. So but by the way, by integrating it we will get the flux. The point is we are not supposed to calculate its magnitude, we just need to look at it, how things are varying, how things are like whether EMF is induced or not. If it is induced, then what will be the direction of the induced current. So we just looking at it like logically or analytically, and like not going for its numerical calculation. So this current carrying wire will produce magnetic field here, direction will be inward, area will be there, so magnetic flux will be linked. And now this loop is moving in this direction. So if this loop after some time, let's say it will be here, is it? Now can you just imagine here, whatever the field is here, exactly same field will be here. Whatever the field is here, exactly same field will be here. Magnetic field here will be exactly same here, and here will be here. So means if I, in simple term, if I say the flux through this coil, this loop, yes, it is there, but it's constant. Flux through loop 1 is constant. So that implies EMF induced will be 0. And if EMF is 0, there will be no current, there will not be any direction of current. So we no need to like comment on the direction of current. So in this situation, flux is there, but it's not changing, and that's why induced EMF in the coil or current in the coil will be 0. So this is about part 1. Next coil is this way. It's placed this way and it's moving. So let's say this is the coil 2 and its initial position is, let's say, this, and after some time its position will be here, right? It's still moving with velocity. Now see, it's initially at this distance. So at this point, magnetic field will be like inversely proportional to R. So here you can see the field will be there and flux will be there. As it's moving here, field will be decreasing. So you can see the flux, it will be inward, but it's decreasing with time because B is changing with R. So as R increases, B will be less, area is constant. So flux phi, if I say it's phi initial, right? Initial, and this is final. So phi initial is greater than phi final. So means this implies changing flux is linked. This implies EMF will be there and current will be there. Next point is what will be the direction of current. So that how we will decide. See, as it's going from here to there, you can see the flux is what? Decreasing. So the induced current should be in a manner such that it try to oppose that. It's decreasing, so it should increase that, right? And flux is in inward direction. You can see if it is current is flowing in anti-clockwise direction, then that flux will be outward, and it will be even like inward flux. And if your like that is decreasing, and if your another flux is outward, then it will decrease it further also, because that flux will be even reduced because negative direction. So if the current is in, let's say, clockwise direction, is it in this direction current, in this situation what will happen? The flux due to this induced current will be inward and it's decreasing, so this current will try to increase that. So this way the direction of current in this loop will be clockwise, is it? So direction of current in the loop will be, loop 2 basically will be clockwise. So I hope you understood the direction, magnetic flux changing, just like logically or like understanding purpose. Numerically we will do the calculation part. So this is just about Faraday's law and some like application. So let's see next.